So my talk is only about bumpless hybrid. I'm going to talk about the site variety, which at this point I hope everybody have no ideas. So if you compute the torus equivalent homology of the site variety, FLN, it is going to be isomorphic to the ring, the x1 up to xn, y1 up to n. Modulo that you generate by you equate the elementary symmetric of X with the elementary symmetric of Y. Like this. And I will note the Schubert class, which is the Poincare dual of the Schubert variety in the fact variety by sigma W. So it's going to be indexed by a permutation in Sn. And there's a presentation of this for which like this class goes to the what's called the double Schubert polynomial. X I of W indexed by W. So this thing will appear, for example, in Alice's talk just now. And so I'm going to give you everyone a quick definition of this like double Schubert polynomial. That's like the algebraic definition. You define a divided difference operator delta I of f to be f minus xi of f divided by xi minus xi plus 1, where xi is the operator that swap xi and xi plus 1. And then you justify like the double Schubert W into the some iterated divided difference operator apply on the one the double Schubert of the longest permutation. The W unites the longest permutation. So this formula is not going to be very important for the talk. I just want to point out one like beauty of this formula is that it has like this minus sign over here. And one property of the double Schubert polynomial that is not going to be obvious from this formulation is that if you plug so the Schubert polynomial as written will not be monomially positive, but if you plug the y, you negate on the y variables, it's going to be monomially positive. And this is definitely not there at all from this formula. So I will give you a different formula from which is this monomial positivity will be clear. So the formula I'm going to give is the bumpless pi ring formula. This is due to lam the DSG monogonal. So what's a bumpless pi ring? So we are going to tile the n by n grid with these 6 allowed tiles. And the rule is, well, I will just draw some example. So the rule is just that when you tile these things, they have to form n pies in total that go from the right end of the square to the bottom end of the square, and they I will assume that the pi rim are reduced, so no 2 pi can cross twice, and for each bumpless pi rim like this, there's an associated permutation. The way you read is you take it's passed from row to column. So for example, row 1 goes to column 3, row 2 goes to column 1. So you read it and you get 3, 1, 4, 2. And the formula is very simple. You just look at the anti-tie. If it's on row I and column J, you get a weight factor of xi minus yj. So for example, for this first one, you should get x1 minus y1 for this box, x1 minus y2 for this box, and then x2 minus y1. Similarly, for this one, you should get x1 minus x2 minus y3. And you can check that, like for the permutation 3142, these are the only two bumpless pi ring associated with that. So if you take the sum of these two, you get the Schubert double Schubert polynomial by this permutation. And so now I want to compute some more general cohomology theory. I want to compute the quantum porous equivalent cohomology of FLN. So you will have more variable, the quantum variable, the 1 up to the n minus 1. The idea has to be changed a bit. I will replace this little e by capital E. I won't have time to explain what it is. And you just put a pill here, the representative class just goes to the quantum double Schubert polynomial. There's also some algebraic difference formula for this, but I will not get into it. What I will tell you is how to compute it using a generalization of the bumpless pi prime, which I will call it, which we would call quantum bumpless pi prime. So how does that formula work? So I will allow 3 more tiles. This one, 2 missing elbow. And this big tile. So this last tile is a domino tile. It's just what it does is just it take up 2 spaces instead of 1. And I have a rule that so basically in the bumpless pi prime case, the pi's only move left and down as they move from the right to the end. In the quantum bumpless pi prime case, I will allow pi to move in 3 directions. I can move left down, I can move left, move down, or move up. I do not allow pi to move to the right. Even though if you mess up with these tiles in the correct way, you can create some objects where the pi move right, but that will not be about the bumpless pi prime. And the weight of these things is this thing, if the top row is I, is going to contribute a qi. And the crossing where the vertical pipe moves up, it will give you a qi. Crossing the pipe where it's just move up without crossing is minus qi. And an elbow like this, it give you this elbow give you a minus qi. So over here I have drawn the 5 quantum bumpless pi prime of 4, 2, 1, 3. The first one is a classical one. The weight is just a classical rule. The second one is similar to the first one, except these 2 boxes have been paired together. So instead of getting these 2 more X, Y weight, you get a Q1 here instead because the top row of this box is on Q1, on row 1. These 2 are the 2 classical weight coming from these 2 boxes. In the third one, you can this pi, you can make it move up like this, and it will take these 2 boxes. Then this elbow over here that will contribute a minus Q1. These 2 are just the classical way. And then of course you can also do the same thing, but you pair it up. So this thing will contribute a Q1, and this thing contribute a minus Q1. The last thing you can do is you can take the pipe over here and you can cross it all the way over like this. This gives you a minus Q1. This gives you a Q2 because it's on row 2. Thank you.
You have a question for Tuong? Yeah, Alan.
To what extent can you do Yang-Baxter, proofs of how does it fit in with the investor formalism of this, or does it?
As far as I know, I don't know how to make it fit into. I do not know any the bumpless pi prime formula. There's some geometric degeneration algorithm that you can use. I don't know one for this. There's also this proof of bumpless pi prime using the 6 vertex model or Yang-Baxter proof. I tried to prove my formula using that. I couldn't figure it out either. So it's just, I don't know.
All right. Let's save further questions for later at night.